Chapter 12 of the Chemistry, Properties and Tests of Precious Stones by John Mastin. This LibriVox recording is in the public domain. Chapter 12. Imitations and some of the Tests of Precious Stones. We now arrive at the point where it is necessary to discuss the manufacture and reformation of precious stones, and also to consider a few of the tests which may be applied to all stones. These are given here in order to save needless repetition. The tests which are specially applicable to individual stones will more properly be found under the description of the stone referred to, so that the present chapter will be devoted chiefly to generalities. With regard to diamonds, the manufacture of these has not as yet been very successful. As will be seen on reference to Chapter 2 on the origin of precious stones, it is generally admitted that these beautiful and valuable minerals are caused by chemically charged water and occasionally, though not always, high temperature, but invariably beautified and brought to the condition in which they are obtained by the action of weight and pressure, extending unbroken through perhaps ages of time. In these circumstances, science, though able to give chemical properties and pressure, cannot of course maintain these continuously for ages. Therefore the chemist must manufacture the jewels in such manner that he may soon see the results of his labours, and though real diamonds may be made, and with comparative ease, from boron in the amorphous or pure state along with aluminium, fused in a crucible at high temperature, these diamonds are but microscopic, nor can a number of them be fused, or in any other way converted into large single stone, so that imitation stones, to be of any service, must be made of a good clear glass. The glass for this purpose is usually composed of 53.70% of red lead, 38.48% of pure quartz in fine powder, preferably water ground, and 7.82% of carbonate of potash, the whole coloured when necessary with metallic oxides of a similar nature to the constituents of the natural stones imitated. But for colourless diamonds the glass requires no such addition to tint it. From the formula given is made the material known as strass or paste, and stones made of it are mostly exhibited under and amongst brilliant artificial lights. The mere fact that they are sold cheaply is prima facie proof that the stones are glass, for it is evident that a diamond, the commercial value of which might be £50 or more, cannot be purchased for a few shillings and be genuine. So long as this is understood and the stone is sold for the few shillings, no harm is done, but to offer it as a genuine stone and at the price of a genuine stone would amount to fraud, and be punishable accordingly. Some of these paste or white stones, as they are called in the trade, are cut and polished exactly like a diamond, and with such success as occasionally to deceive all but experts. Such imitations are costly, though of course not approaching the value of the real stones, it being no uncommon thing for valuable jewels to be duplicated in paste, whilst the originals are kept in a strong room of a bank or safe deposit. In all cases, however, a hard file will abrade the surface of the false stone. In Chapter 7 we found that quartz is in the 7th degree of hardness, and an ordinary file is but a shade harder than this, so that almost all stones higher than number 7 are unaffected by a file unless it is used roughly, so as to break a sharp edge. In order to prepare artificial diamonds and other stones for the file and various tests, they are often what is called converted into doublets or triplets. These are made as follows: the body of the glass is paste, and on the table, see last chapter, and perhaps on the broader facets, there will be placed a very thin slab of the real stone, attached by cement. In the case of the diamond the body is clear, but in the coloured imitations the paste portion is made somewhat lighter in shade than the real stone would be, the portion below the girdle being coloured chemically, or mounted in a coloured backing. Such a stone will of course stand most tests, for the parts usually tested are genuine. A stone of this nature is called a doublet, and it is evident that when it is tested on the underside it will prove too soft. Therefore the triplet has been introduced. This is exactly on the lines of the doublet, except that the collet and perhaps the pavilions are covered also, so that the girdle, which is generally encased by the mounting, is the only surface portion of paste. In other cases the whole of the crown is genuine, whilst often both the upper and lower portions are solid and genuine, the saving being effected by using a paste centre at the girdle, covered by the mounting. Such a stone as this last mentioned is often difficult to detect without using severe tests and desperate means. For example, A, by its crystalline structure, see Chapter 3, B. By the cleavage planes, see Chapter 4, C. By the polariscope, see Chapter 5, D. By the dichroscope, see Chapter 6, E. By specific gravity, see Chapter 8, F. Cutting off the mounting and examining the girdle, G. Soaking the stone for a minute or so in a mixture said to have been originally discovered by M. D. Rothschild and composed of hydrofluoric acid and ammonia. This will not answer for all stones, but is safe to use for the diamond and a few others. Should the jewel be glass, it will be etched, if not completely destroyed, but if genuine, no change will be apparent. H. Soaking the diamond for a few minutes in warm or cold water, in alcohol, in chloroform, or in all these in turn, when, if a doublet or triplet, it will tumble to pieces where joined together by the cement, which will have been dissolved. It is, however, seldom necessary to test so far, for an examination under the microscope, even with low power, is usually sufficient to detect in the glass the air bubbles which are almost inseparable from glass mixtures, though they do not detract from the physical properties of the glass. The higher powers of the same instrument will almost always define the junction and the layer or layers of cement, no matter how delicate a film may have been used. Any one of these tests is sufficient to isolate a false stone. Some of the softer genuine stones may be fused together with splinters, dust, and cuttings of the same stones, and of this product is formed a larger stone, which, though manufactured, is essentially perfectly real, possessing exactly the same properties as a naturally formed stone. Many such stones are obtained as large as an ordinary pin's head, and are much used commercially for cluster work in rings, brooches, for watch jewels, scarf pins, and the like, and are capable of being cut and polished exactly like an original stone. This is a means of using up to great advantage the lapidary's dust, and though these products are real stones, perhaps a little more enriched in colour chemically, they are much cheaper than a natural stone of the same size and weight. Some spurious stones have their colour improved by heat, by being tinged on the outside, by being tinted throughout with a fixed colour and placed in a clear setting. Others again have a setting of a different hue, so that the reflection of this shall give additional colour and fire to the stone. For instance, glass diamonds are often set with the whole of the portion below the girdle hidden, this part of the stone being silvered like a mirror. Others are set open, being held at the girdle only, the portion covered by the setting being silvered. Other glass imitations, such as the opal, have a tolerably good representation of the fiery opal given to them by the admixture, in the glass, of a little oxide of tin, which makes it somewhat opalescent, and in the setting is placed a backing of red, gold, copper, or fiery-coloured tinsel, whilst the glass itself at the back is painted very thinly with a paint composed of well-washed and dried fish scales, reduced to an impalpable powder, mixed with a little pure, refined mastic or other colourless varnish. This gives a good imitation of phosphorescence, as well as a slight pearliness, whilst the tinsel, seen through the paint and the curious milkiness of the glass, gives good fire. A knowledge of the colours natural to precious stones and to jewels generally is of great service in their rough classification for testing, even though some stones are found in a variety of colours. An alphabetical list of the most useful is here appended, together with their average specific gravities and hardness. See also Chapter 7 on Hardness and Chapter 8 on specific gravity. White or colourless stones. Beryl, hardness 7 3/4, specific gravity 2.709 to 2.81. Corundum, hardness 9, specific gravity 3.90 to 4.16. Diamond, hardness 10, specific gravity 3.502 to 3.564. Jade, hardness 7, specific gravity 3.300 to 3.381. Opal, hardness 5.5 to 6.5, specific gravity 2.160 to 2.283. Phenakite, hardness 7 3/4, specific gravity 2.965. Quartz, hardness 7, specific gravity 2.670. Rock crystal, hardness 7, specific gravity 2.521 to 2.795. Sapphire, hardness 9, specific gravity 4.049 to 4.060. Spinel, hardness 8, specific gravity 3.614 to 3.654. Topaz, hardness 8, specific gravity 3.500 to 3.520. Tourmaline, hardness 7 1/4, specific gravity 3.029. Zircon, hardness 7 1/2, specific gravity 4.700 to 4.880. Yellow stones. Amber, hardness 2 1/2, specific gravity 1.000. Beryl, hardness 7 3/4, specific gravity 2.709 to 2.810. Chrysoberyl, hardness 8 1/2, specific gravity 3.689 to 3.752. Chrysolite, hardness 6 to 7, specific gravity 3.316 to 3.528. Corundum, the yellow variety known as Oriental Topaz, not topaz, see below. Hardness 9, specific gravity 3.90 to 4.16. Diamond, hardness 10, specific gravity 3.502 to 3.564. Garnets various, hardness 6 1/2 to 7 1/2, specific gravity 3.4 to 4.5. Hyacinth, a form of zircon, hardness 7 1/2, specific gravity 4.7 to 4.88. Quartz, citrine, hardness 7, specific gravity 2.658. Sapphire, hardness 9, specific gravity 4.049 to 4.060. Spinel, hardness 8, specific gravity 3.614 to 3.654. Topaz, for Oriental Topaz, see above, hardness 8, specific gravity 3.500 to 3.520. Tourmaline, hardness 7 1/4, specific gravity 3.210. Brown and flame-coloured stones. Andalusite, hardness 7 1/2, specific gravity 3.204. Diamond, hardness 10, specific gravity 3.502 to 3.564. Garnets various, hardness 6 1/2 to 7 1/2, specific gravity 3.40 to 4.50. Hyacinth, a form of zircon, see below, hardness 7 1/2, specific gravity 4.70 to 4.88. Quartz, smoke-coloured, hardness 7, specific gravity 2.670. Tourmaline, hardness 7 1/4, specific gravity 3.100. Zircon, hyacinth, hardness 7 1/2, specific gravity 4.70 to 4.88. Red and rose-coloured stones. Carnelian, a variety of chalcedony, hardness 6 1/2, specific gravity 2.598 to 2.610. Diamond, hardness 10, specific gravity 3.502 to 3.564. Deep red garnet, hardness 7 1/4, specific gravity 3.40 to 4.50. Jasper, hardness 7, specific gravity 2.668. Opal, the fire opal, hardness 5 1/2 to 6 1/2, average, specific gravity 2.21. Ruby, hardness 9, specific gravity 4.073 to 4.080. Rhodonite, hardness 5 1/2 to 6 1/2, specific gravity 3.413 to 3.617. Sapphire, hardness 9, specific gravity 4.049 to 4.060. Spinel ruby, hardness 8, specific gravity 3.614 to 3.654. Topaz, hardness 8, specific gravity 3.500 to 3.520. Tourmaline, hardness 7 1/4, specific gravity 3.024. Zircon, hardness 7 1/2, specific gravity 4.70 to 4.88. Pink stones. Beryl, hardness 7 3/4, specific gravity 2.709 to 2.810. Diamond, hardness 10, specific gravity 3.502 to 3.564. Ruby, hardness 9, specific gravity 4.073 to 4.080. Spinel, hardness 8, specific gravity 3.614 to 3.654. Topaz, burnt or pinked, see chapter 14, page 92, hardness 8, specific gravity 3.500 to 3.520. Tourmaline, hardness 7 1/4, specific gravity 3.024. Bluestones, beryl, hardness 7 3/4, specific gravity 2.709 to 2.810. Diamond, hardness 10, specific gravity 3.502 to 3.564. Dichorite, water sapphire, hardness 7 to 7 1/2, specific gravity 4.049 to 4.060. Dysthene, kyanite, hardness 5 to 7, specific gravity 3.609 to 3.688. Iolite, cordiorite, hardness 7 1/4, specific gravity 2.641. Lapis Lazuli, hardness 5 1/2, specific gravity 2.461. Sapphire, hardness 9, specific gravity 4.049 to 4.060. Topaz, hardness 8, specific gravity 3.500 to 3.520. Tourmaline, hardness 7 1/4, specific gravity 3.160. Turquoise, hardness 6, specific gravity 2.800. Greenstones, aquamarine, hardness 7 3/4, specific gravity 2.701 to 2.800. Chrysoberyl, hardness 8 1/2, specific gravity 3.689 to 3.752. Chrysolite, hardness 6 to 7, specific gravity 3.316 to 3.528. Chrysoprase, quartz, hardness 7, specific gravity 2.670. Diamond, hardness 10, specific gravity 3.502 to 3.564. Dioptase, hardness 5, specific gravity 3.289. Emerald and Oriental Emerald, hardness 7 3/4, specific gravity 2.690. Euclase, hardness 7 1/2, specific gravity 3.090. Garnet, see also red garnet, hardness 6 1/2 to 7 1/2, specific gravity 3.400 to 4.500. Heliotrope, chalcedony, hardness 6 1/2, specific gravity 2.598 to 2.610. Hiddenite, a variety of spodumene, hardness 6 1/2 to 7, specific gravity 3.130 to 3.200. Jade, hardness 7, specific gravity 3.300 to 3.381. Jadeite, hardness 7, specific gravity 3.299. Malachite, hardness 3 1/2, specific gravity 3.710 to 3.996. Peridot, a variety of chrysolite, hardness 6 to 7, specific gravity 3.316 to 3.528. Plasma, a variety of chalcedony, hardness 6 1/2, specific gravity 2.598 to 2.610. Quartz, hardness 7, specific gravity 2.670. Sapphire, hardness 9, specific gravity 4.049 to 4.060. Topaz, hardness 8, specific gravity 3.500 to 3.520. Tourmaline, hardness 7 1/4, specific gravity 3.148. Violet stones. Amethyst, hardness 7, specific gravity 2.661. Diamond, hardness 10, specific gravity 3.502 to 3.564. Quartz, amethyst, hardness 7, specific gravity 2.670. Sapphire, hardness 9, specific gravity 4.049 to 4.060. Spinel, hardness 8, specific gravity 3.614 to 3.654. Tourmaline, hardness 7 1/4, specific gravity 3.160. Chatoyant stones. These stones are easily recognizable by their play of colour. See Chapter 14. Black stones. Diamond, hardness 10, specific gravity 3.502 to 3.564. Garnet, hardness 6.5 to 7.5, specific gravity 3.400 to 4.500. Jet, hardness 3.5, specific gravity 1.348. Onyx, a variety of chalcedony, hardness 6.5, specific gravity 2.598 to 2.610. Quartz, hardness 7, specific gravity 2.670. Tourmaline, not unlike black resin in appearance, hardness 7.25, specific gravity 3.024 to 3.300. End of Chapter 12. Chapter 13 of the Chemistry, Properties and Tests of Precious Stones by John Mastin. This LibriVox recording is in the public domain. Chapter 13. Various Precious Stones. The Diamond. To recapitulate certain of the facts respecting the diamond, this wonderful gem has the distinction amongst precious stones of being unique. Though many are composed of 2, 3, or but a small number of elements, the diamond is the only stone known consisting of one element, and absolutely nothing else. Pure crystallized carbon. Its hardness is proverbial. Not only is it untouched by the action of a hard file, but it occasionally refuses to split when struck with finely tempered steel, which it often causes to break. Such was the case with the South African diamond, for when the knife that was to break it was struck smartly with a steel bar, the first blow broke the blade without affecting the diamond, yet a piece of bort or diamond dust, splinters or defective diamonds, all these being called bort, may readily be pulverized in a hard steel mortar with a hard steel pestle. The diamond is the hardest stone known. It is also the only stone known which is really combustible. It is of true adamantine lustre, classed by experts as midway between the truly metallic and the purely resinous. In refractive power and dispersion of the coloured rays of light called its fire, it stands pre-eminent. It possesses a considerable variety of colour. That regarded as the most perfect and rare is the blue-white colour. Most commonly, however, the colours are clear, with steely blue casts, pale and neutral colour yellow, whilst amongst the most expensive and rare are those of green, pale pink, red, and any other variety with strong and decided colour. Although these stones are sold by the carat, there can be no hard and fast rule laid down as to the value of a carat, for this depends on the size, quality, and the purity of the stone. The larger the stone, the greater the value per carat, and prices have been known to range from £25 per carat for a small stone to £500 per carat for a large one, whereas the exceptionally large stones possess a value almost beyond estimation. It often happens that some stones, particularly those from South Africa and Brazil, are tinted when uncut, probably by reason of the action upon them of their matrix, especially if ironstone, or with rolling for ages amongst ironstone in river beds, which gives them a slight metallic appearance. In each case the cause is suggested by the fact that these tinted stones are usually found in such places, and that the tinting is very thin and on the surface only, so that the cutting and shaping of the stone gets below it to the perfectly clear diamond. From Pliny and other historians we gather that at various periods considerable superstition has existed with regard to diamonds, such as that if one is powdered it becomes poisonous to a remarkable degree, that gifts of diamonds between lovers, married and unmarried, produce and seal affection, hence the popularity of diamonds in betrothal rings. Pretty as is the conceit, there is no doubt about the fact that the gift of diamonds to the object of one's affections does usually produce a feeling of pleasure to both parties, from which it would appear that there is some ground for the belief. Corundum. This mineral is a species of crystal or crystalline alumina, an almost pure anhydrous alumina, Al2O3, in many varieties both of shape and colour. The chief stone is the ruby, considered when large to be of even more importance and value than the diamond. there are many other red stones in this group. Sapphires also are a species of corundum, both the blue and the colourless varieties, as are also the aquamarine, the emerald, the amethyst, the topaz, and others, all of widely differing colour, as well as the star-shaped or aster ruby, called the ruby cat's eye. All these vary more in colour than in their chemical properties. Still another variety, greyish-black, and generally associated with hematite iron ore, is called emery, and when ground in different degrees of fineness is so well known by its general use as a polishing medium as to need no description. It should, however, be mentioned that amongst the more coarsely ground emery it is no uncommon thing to find minute sapphires, taking sapphires in their broad commercial meaning as signifying any variety of corundum except the red and the emery. The surface of crystals of corundum are often clouded or dull, whilst its classification of lustre is vitreous. It is double refracting and has no cleavage. It is found in China, India, Burma, Ceylon, South Africa, America, and in many other places, having a wide distribution. The ruby. In the dichroscope, the ruby shows two images, one square of a violet red, the second square being a truer and a paler red. It may be subjected to strong heat, when it changes its colour to a sooty or dirty slate, this varying with the locality in which the stone is found, and the manner in which the heat is applied, but as it cools it becomes paler and greener, till it slowly enrichens. The green first becomes broken, then warmer, redder, and finally assumes its original beautiful blood red. This method of heating is sometimes used as a test, but it is a test which often means the complete ruin of a stone which is not genuine. Another characteristic which, in the eyes of the expert, invariably isolates a real from an artificial ruby is its curious mild brilliance, which as yet has not been reproduced by any scientific method in paste or any other material, but perhaps the safest test of all is the crystalline structure, which identical structure appears in no other stone, though it is possible, by heating alumina coloured with oxide of iron, and perhaps also a trace of oxide of chromium to a very high temperature for a considerable time, and then cooling very slowly, to obtain a ruby which is nearly the same in its structure as the real gem. Its specific gravity and hardness may perhaps be to standard, and when properly cut its brilliance would deceive all but an expert. And as in some real rubies there are found slight hollows, corresponding or analogous to the bubbles found in melted glass, it becomes a matter of great difficulty to distinguish the real from the imitation by such tests as hardness, specific gravity, dichroism, and the like, so that in such a case, short of risking the ruin of the stone, ordinary persons are unable to apply any convincing tests. Therefore only the expert can decide, by his appreciation of the delicate shade of difference in the light of a true ruby, and that of an excellent imitation, and by the distribution of the colour, which, however experienced the chemist may be, or with what care the colouring matter may have been incorporated in the mass, has been found impossible of distribution throughout the body of an artificial stone, so perfectly and in the same manner and direction as nature herself distributes it in the genuine. This alone, even in the closest imitations, is clear to the eye of the expert, though not to the untrained eye, unless the stone is palpably spurious. To one who is accustomed to the examination of precious stones, however perfect the imitation, it is but necessary to place it beside or amongst one or more real ones for the false to be almost instantly identified, and that with certainty. The sapphire. The sapphire is not so easy to imitate, as its hardness exceeds that of the ruby, and imitations containing its known constituents, or of glass, are invariably softer than the natural stone. As before remarked, almost any form of corundum other than red is, broadly, called sapphire, but giving them their strictly correct designations, we have the olivine corundum, called chrysolite, oriental, which is harder than the ordinary or noble chrysolite, sometimes called the peridot. The various yellow varieties of corundum take the name of the oriental topaz, which, like most, if not all, the corundum varieties, is harder than the gem which bears the same name, minus the prefix oriental. Then we have the amethyst sapphire, which varies from a red to a blue-purple, being richer in colour than the ordinary amethyst, which is a form of violet-coloured quartz, but the corundum variety, which, like its companions, is called the oriental amethyst, is both rarer and more precious. A very rare and extremely beautiful green variety is called the Oriental Emerald. The Oriental Jacinth or Hyacinth is a brown-red corundum, which is more stable than the ordinary hyacinth, this latter being a form of zircon. It changes colour on exposure to light, which colour is not restored by subsequent retention in darkness. The blue sapphire is of all shades of blue, from cornflower blue to the very palest tints of this colour, all the gradations from light to dark purple blues, and in fact so many shades of tone and colour that they become almost as numerous as the stones. These stones are usually found in similar situations to those which produce the ruby, and often along with them. The lighter colours are usually called females or feminine stones, whilst the darker ones are called masculine stones. Some of these dark ones are so deep as to be almost black, when they are called ink sapphires, and if inclining to blue, indigo sapphires, in contradistinction to which the palest of the stones are called water sapphires. The colouring matter is not always even, but is often spread over the substance of the stone in scabs or splotches, which rather favours imitation, and where this unevenness occurs it may be necessary to cut or divide the stone, or so to arrange the form of it that the finished stone shall be equally blue throughout. In some cases, however, the sapphire may owe its beauty to the presence of 2, 3 or more colours in separate strata appearing in one stone, such as a portion being a green-blue, another cornflower blue, another perfectly colourless, another a pale sky-blue, another yellow, each perfectly distinct, the stone being cut so as to show each colour in its full perfection. This stone, the sapphire, is hardness number 9, see Hardness table, and therefore ranks next to the diamond, which makes it a matter of great difficulty to obtain an imitation which is of the same specific gravity, and of the same degree of hardness, though this has been done. Such stones are purchasable, but though sold as imitations at comparatively low price, and the buyer may consider them just as good as the real gem, to the experienced eye they are readily detectable. By heating a sapphire, its blue colour slowly fades, to complete transparency in many cases, or at any rate to so pale a tint as to pass for a transparent stone. Valuable as is the sapphire, the diamond is more so, and it follows that if one of these clear or cleared sapphires is cut in the rose or brilliant form, which forms are reserved almost exclusively for the diamond, such a stone would pass very well as a diamond, and many so cut are sold by unscrupulous people as the more valuable stone, which fraud an expert would of course detect. Sapphires are mentioned by Pliny, and figure largely in the ancient history of China, Egypt, Rome, etc. The Greeks dedicated the sapphire especially to Jupiter, and many of the stones were cut to represent the god. It also figured as one of the chief stones worn by the Jewish high priest on the breastplate. Some stones have curious rays of variegated colour due to their crystalline formation, taking the shape of a star. These are called asteriated or cat's eye sapphires. Others have curious flashes of light, technically called a play of light, as described in Chapter 6 on colour, together with a curious blue opalescence. These are the girasol. Another interesting variety of this blue sapphire is one known as Chatoyant. This has a rapidly changing lustre, which seems to undulate between a green-yellow and a luminous blue, with a phosphorescent glow or fire, something like that seen in the eyes of a cat in the dark, or the steady burning glow observed when a cat is fascinating a bird, hence its name. This is not the same variety of the asteriated or cat's eye or lynx eye mentioned above. End of Chapter 13. Chapter 14 of the Chemistry, Properties and Tests of Precious Stones by John Mastin. This LibriVox recording is in the public domain. Chapter 14 Various Precious Stones, continued. The chrysoberyl. There are certain stones and other minerals which, owing to their possession of numerous microscopically fine cavities of a globular or tubular shape, have the appearance of rays or stars, and these are called asteriated. Several of such stones have been discussed already in the last chapter, and in addition to these star-like rays, some of the stones have, running through their substance, one or more streaks, perhaps of asbestos or calcite, some being perfectly clear whilst others are opalescent. When these streaks pass across the star-like radiations they give the stone the appearance of an eye, the rays forming the iris, the clear opalescent or black streak closely resembling the slit in a cat's eye, and when these stones are cut en cabochon, that is dome-shaped, see Chapter 11 on cutting, there is nothing to deflect the light beams back and forth from facet to facet, as in a diamond, so that the light, acting directly on these radiations or masses of globular cavities and on the streak, causes the former to glow like living fire, and the streak appears to vibrate, palpitate, expand and contract, exactly like the slit in the eye of a cat. There are a considerable number of superstitions in connection with these cat's eye stones, many people regarding them as mascots, or with disfavour, according to their colour. When possessing the favourite hue or fire of the wearer, such as the fire of the opal for those born in October, of the ruby for those born in July, etc., these stones are considered to bring nothing but good luck, and to ward off accident, danger, and sudden death, to be a charm against being bitten by animals, and to be a protection from poison, the evil eye, etc. They figured largely, along with other valuable jewels, in the worship of the ancient Egyptians, and have been found in some of the tombs in Egypt. They also appeared on the sistrum, which was a sacred instrument used by the ancient Egyptians in the performance of their religious rites, particularly in their sacrifices to the goddess Isis. This therefore may be considered one of their sacred stones, whilst there is some analogy between the cat's eye stones and the sacred cat of the Egyptians, which recur so often in their hieroglyphics. It is well known that our domestic cat is not descended from the wild cat, but from the celebrated cat of Egypt, where history records its being domesticated at least 13 centuries BC. From there it was taken throughout Europe, where it appeared at least a century BC, and was kept as a pet in the homes of the wealthy, though certain writers, speaking of the mouse hunters of the old Romans and Greeks, state that these creatures were not the Egyptian cat, but a carnivorous long-bodied animal, after the shape of a weasel, called Martin, of the species the beech or common martin, Mustela foina, found also in Britain today. It is also interesting to note that the various superstitions existing with regard to the different varieties and colours of cats also exist in an identical manner with the corresponding colours of the minerals known as cat's eye. Several varieties of cat's eye have already been described. Another important variety is that of the chrysoberyl called cymophane. This is composed of glucina, which is glucinum oxide, or beryllia, BeO, of which there is 19.8%, and alumina, or aluminium oxide, Al2O3, of which there is 80.2%. It has, therefore, the chemical formula BeO, Al2O3. This stone shows positive electricity when rubbed, and unlike the sapphires described in the last chapter, which lose their colour when heated, this variety of chrysoberyl shows no change in colour, and any electricity given to it, either by friction or heat, is retained for a long time. When heated in the blowpipe alone it remains unaltered, that is, it is not fusible, and even with microcosmic salt it requires a considerably long and fierce heat before it yields and fuses, and acids do not act upon it. It crystallises in the fourth rhombic system, and its lustre is vitreous. The cymophane shows a number of varieties, quite as many as the chrysoberyl, of which it is itself a variety, and these go through the gamut of greens, from a pale white green to the stronger green of asparagus, and through both the grey and yellow greens to dark. It is found in Ceylon, Moravia, the Ural Mountains, Brazil, North America, and elsewhere. The cat's eye of this is very similar to the quartz cat's eye, but a comparison will make the difference so clear that they could never be mistaken, apart from the fact that the quartz has a specific gravity considerably lower than the chrysoberyl cat's eye, which latter is the true cat's eye, and the one usually understood when allusion is made to the stone without any distinguishing prefix, such as the ruby, sapphire, quartz, etc. cat's eye. It should, however, be mentioned that this stone is referred to when the names Ceylonese and Oriental cat's eye are given, which names are used in the trade as well as the simple appellation cat's eye. One peculiarity of some of these stones is that the fire, or glow, is usually altered in colour by the colour of the light under which it is seen, the change of colour being generally the complementary. Thus a stone which in one light shows red in another will be green. The eye, showing blue in one light, will become orange in another, whilst the yellow of another stone may show a decided purple or amethyst in a different light. A good test for this, and indeed most precious stones, is that they conduct heat more quickly than does glass, and with such rapidity that on breathing upon a stone the warmth is conducted instantly, so that, though the stone is dimmed, the dimness vanishes at once, whereas with glass the film of moisture fades but slowly in comparison. The topaz. The name topaz is derived from the Greek topazos, which is the name of a small island situated in the Gulf of Arabia, from whence the Romans obtained a mineral which they called topazos and topazion, which mineral today is termed chrysolite. The mineral topaz is found in Cornwall and in the British Isles generally, also in Siberia, India, South America, and many other localities, some of the finest stones coming from Saxony, Bohemia, and Brazil, especially the last named. The cleavage is perfect and parallel to the basal plane. It crystallizes in the fourth rhombic system, its lustre is vitreous, it is transparent or ranging from that to translucent, the streak is white or colourless, its colour varies very much. Some stones are straw colour, some are grey, white, blue, green, and orange. A very favourite colour is the pink, but in most cases this colour is not natural to the stone, but is the result of burning or pinking, as the process is called technically, which process is to raise the temperature of a yellow stone till the yellow tint turns to a pink of the colour desired. The topaz is harder than quartz, as will be seen on reference to the hardness table, and is composed of a silicate of aluminium, fluorine taking the place of some of the oxygen. Its composition averages 16.25% of silica, 55.75% of alumina, or oxide of aluminium, and fluoride of silicium 28%. Its formula is (Al, round brackets F, OH, close round brackets, close square brackets 2, SiO4, or round brackets AlF, close brackets 2, SiO4. From this it will be understood that the fluorine will be evolved when the stone is fused. It is, however, very difficult to fuse, and alone it is infusible under the blowpipe, but with microcosmic salt it fuses and evolves fluorine, and the glass of the tube in the open end of which the stone is fixed is bitten with the gas. Such experiments with topaz are highly interesting, and if we take a little of the powdered stone and mix it with a small portion of the microcosmic salt, we may apply the usual test for analysing and proving aluminium. Thus, a strongly brilliant mass is seen when hot, and if we moisten the powder with nitrate of cobalt and heat again, this time in the inner flame, the mass becomes blue. Other phenomena are seen during the influence of heat. Some stones, as stated, become pink on heating, but if the heating is continued too long or too strongly, the stone is decoloured. Others again suffer no change, and this has led to a slight difference of opinion amongst the chemists as to whether the colour is due to inorganic or organic matter. Heating also produces electricity, and the stone, and even splinters of it, will give out a curious phosphorescent light, which is sometimes yellow, sometimes blue or green. Friction or pressure produces strong electrification. Thus the stones may be electrified by shaking a few together in a bag, or by the tumbling of the powdered stone grains over each other as they roll down a short inclined plane. The stones are usually found in the primitive rocks, varying somewhat in different localities in their colour. Many of the Brazilian stones, when cut as diamonds, are not unlike them. In testing, besides these qualities already enumerated, the crystalline structure is specially perfect and unmistakable. It is doubly refractive, whereas spinel and the diamond, which two it closely resembles, are singly refractive. Topaz is readily electrified, and, if perfect at terminals, becomes polarized. Also the commercial solution of violets, of which a drop only need be taken for a test, is turned green by adding to it a few grains of topaz dust, or of a little splinter crushed to a fine powder. The beryl. The beryl is a compound of silicates of beryllia and alumina, with the formula 3BeOSiO2 plus Al2O3, 3SiO2, or 3BeO Al2O3, 6SiO2. It differs very little indeed from the emerald, with the exception of its colour. In the ordinary varieties this is somewhat poor, being mostly blue, or a dirty or a greenish yellow. The better kinds, however, possess magnificent colour and variety, such as the aquamarine, emerald, etc. The cleavage is parallel to the basal plane. Its lustre is sometimes resinous, sometimes vitreous, and it crystallises in the second hexagonal system. It occurs in somewhat long hexagonal prisms, with smooth truncated planes, and is often found in granite and the silt brought down by rivers from granite, gneiss, and similar rocks. It is found in Great Britain and in many parts of Europe, Asia, and America, in crystals of all sizes, from small to the weight of several tons. The common kinds are too opaque and colourless to be used as gems, and are somewhat difficult of fusion under the blowpipe, on the application of which heat some stones lose their colour altogether. Others partly, others, which before heating were somewhat transparent, become clouded and opaque. Others suffer no change in colour, whilst some are improved. In almost every case a slight fusion is seen on the sharp edges of fractures, which become smooth, lose their sharpness, and have the appearance of partly fused glass. The hardness varies from 7 1/4 to 8, the crystals being very brittle, breaking with a fracture of great unevenness. The better varieties are transparent, varying from that to translucent, and are called the noble beryls. Transparent beryl crystals are used by fortune tellers as gazing stones, in which they claim to see visions of future events. The emerald. Considering the particular emerald, which is a variety of beryl, although the name emerald in the trade is applied somewhat loosely to any stone which is of the same colour, or approaching the colour of the beryl variety, this emerald only differs chemically from the beryl, just described, in possessing an addition of oxide of chromium. In shape, crystallization, fracture and hardness it is the same, and often contains, in addition to the chromium, the further addition of traces of carbonate of lime, magnesia, and occasionally faint traces of hornblende and mica, which evidently result from its intimate association with the granite rock and gneiss, amongst which it is mostly found, the latter rocks being of a slaty nature, in layers or plates, and like granite, containing mica, pyrites, felspar, quartz, etc. Emeralds have been known from very early times, and are supposed to have been found first in the mines of ancient Egypt. They were considered amongst the rarest and the most costly of gems, and it was the custom, when conferring lavish honour, to engrave or model emeralds for presentation purposes. Thus we find Pliny describes Ptolemy giving Lucullus, on his landing at Alexandria, an emerald on which was engraved his portrait. Pliny also relates how the short-sighted Nero watched the fights of gladiators through an eyeglass made of an emerald, and in ancient times, in Rome, Greece, and Egypt, eyeglasses made of emeralds were much valued. Many of these, as well as engraved and carved emeralds, have been discovered in ruins and tombs of those periods. The copper emerald is rare. It is a hydrous form of copper silicate, CuOSiO2 plus H2O, of a beautiful emerald green, varying from transparent to translucent. It exhibits double refraction, and is crystallized mineral, brittle, and showing a green streak. This is less hard than the real emerald. It is heavier, deeper in colour, and is usually found in crystals in cavities of a particular kind of limestone, which exists at Altin Tube, a hill in the Altai Mountains, in the Urals, and in North and Central America. The tourmaline. The tourmaline is a most complex substance. Almost every stone obtained has a different composition, some varying but slightly, with mere traces of certain constituents which other stones possess in a perceptible degree. Consequently, it is not possible to give the chemical formula, which might, and possibly would, be found but seldom, even in analyses of many specimens. It will therefore be sufficient to state the average composition, which is ferrous oxide, manganous oxide, potash, lime, boracic acid, magnesia, soda, lithia, and water. These form, roughly speaking, 25% of the bulk, the remainder being oxide of silicon and oxide of aluminium in about equal parts. It crystallizes in the second hexagonal system with difficult cleavage and vitreous lustre. It will naturally be expected that a substance of such complexity and variety of composition must necessarily have a corresponding variety of colour. Thus we find in this, as in the corundum, a wonderful range of tints. The common is the black, which is not used as a gem. Next come the colourless specimens, which are not often cut and polished, whereas all the transparent and coloured varieties are in great demand. To describe adequately their characteristics with relation to light would alone require the space of a complete volume, and the reader is referred to the many excellent works on physics, optics, which are obtainable. This stone is doubly refracting, exhibiting extremely strong dichroism, especially in the blue and the green varieties. It polarises light, and when viewed with the dichroscope, shows a remarkable variety of twin colours. It will be remembered that in Hogarth's Rake's Progress, the youth is too engrossed in the changing wonders of a tourmaline to notice the entrance of the officers come to arrest him. End of chapter 14. Chapter 15 of the Chemistry, Properties and Tests of Precious Stones by John Mastin. This LibriVox recording is in the public domain. Chapter 15. Various Precious Stones continued. Zircon. Zircon appears to have been first discovered by Klaproth in 1789 in the form of an earth, and 6 years later he found that the stone hyacinth contained a similar substance, both having the formula ZrSiO4, and both having as their colouring agent ferric oxide. There are several methods of obtaining the metallic element zirconium. It is, however, with the silicate of zirconium that we have to deal at the moment. This is called zircon, ZrSiO4, or hyacinth when transparent or red, but when smoke-coloured or colourless it is the jargoon or jarcon, and is found in silt and alluvial soils, limestone, gneiss and various forms of schist in India, Australia, the Urals and certain parts of America. It is often combined with and found in juxtaposition to gold and certain varieties of precious stones. The lines of cleavage are parallel to the sides of the prism, and the crystals have an adamantine or diamond lustre, varying from the completely opaque to the transparent. In some varieties the oxide of uranium is also present in traces. It crystallises in the third tetragonal system with indistinct cleavage. Its specific gravity varies from 4.70 to 4.88 according to the specimen and the locality. This stone, like some of the others described, has a very wide range of colour, going through reds, browns, greens, yellows, oranges, whites, greys, blues, from light to indigo, notwithstanding which it is somewhat difficult to imitate scientifically, though its composition of 33% of silica with 67% of zirconia, the oxide of zirconium, is practically all it contains apart from the colouring matter, such as the metallic oxides of iron, uranium, etc. Its hardness is 7.5, consequently it is untouched by a file, and so far, if one or perhaps two of the three qualities of colour, hardness and specific gravity are obtained in a chemically made zircon, the third is wanting. Under the blowpipe, zircons are infusible, but the coloured stones, when heated strongly, become heavier, and as they are contracting their colour fades, sometimes entirely, which changes are permanent, so that, as they possess the adamantine lustre, they are occasionally cut like a diamond, and used as such, though their deficiency in fire and hardness, and their high specific gravity, make them readily distinguishable from the diamond. On exposure to light, the coloured zircon becomes more or less decoloured, especially is this so in sunlight, for when the direct rays of the sun fall upon it, the colours fade, and for a moment or two occasional phosphorescence follows, as is the case when the stone is warmed or heated in a dark room. The stone appears to be very susceptible to brilliant light rays, and in certain specimens which were split for testing, 1/2 of each being kept excluded from light for purposes of comparison, it was found that sunshine affected them most, then brilliant acetylene gas, which was more effective still when tinted yellow by being passed through yellow glass. The electric arc was not so effective, but the electric light of the mercury vapour lamp, though causing little change at the first, after a few hours' exposure rapidly bleached certain of the colours, whilst having no effect on others. Coal gas with incandescent fibre mantle was slightly effective, whilst the coal gas burned direct through an ordinary burner affected very few of the colours, even after 24 hours' exposure at a distance of 3 feet. In all these cases, though the colours were slightly improved by the stones being kept for a time in the dark, they failed to recover their original strength, showing permanent loss of colour. The silicates. The chief of these are the garnets, crystallising in the cubic system and anhydrous. The garnet is usually in the form of a rhombic dodecahedron, or as a trisoctahedron, called also sometimes an icosatetrahedron, or a mixture of the two, though the stones appear in other cubic forms. In hardness they vary from 6½ to 8½. They average from 40 to about 42% of silica, the other ingredients being in fairly constant and definite proportions. They are vitreous and resinous in their lustre, and of great variety of colour, chiefly amongst the reds, purples, violets, greens, yellows, and blacks, according to the colouring matter present in their mass. There are many varieties which are named in accordance with one or more of their constituents, the best known being A. The iron alumina garnet, having the formula 6FeO, 3SiO2 plus 2AlO3, 3SiO2. This is the precious garnet, or almandine, sometimes called the Oriental Garnet. These stones are found in Great Britain, India, and South America, and are deep red and transparent, of vitreous lustre. They get up well, but certain varieties are so subject to defects in their substance, brought about by pressure, volcanic action, and other causes, some of which are not yet known, that their quality often becomes much depreciated in consequence. This inferior variety of the iron alumina garnet is called the common garnet, and has little lustre, being sometimes opaque. The perfect qualities, or almandine, as described above, are favourite stones with jewellers, who mount great quantities of them. The second variety is the B lime iron garnet, formula 6CaO, 3SiO2 plus 2Fe2O3, 3SiO2. The chief of this class is the melanite, sometimes dull, yet often vitreous. It is mostly found in volcanic rocks, such as tuff. This variety is very popular with jewellers for mourning ornaments, for as it is a beautiful velvet black in colour and quite opaque, it is pre-eminent for this purpose, being considerably less brittle than jet, though heavier. Another variety is the topazolite, both yellow and green. The aplome is greenish-yellow, yellowish-green, brown, and usually opaque. A further form of lime iron garnet is the pyrenite, first found in the Pyrenees mountains, hence its name. The C lime chrome garnets, 6CaO, 3SiO2 plus 2Cr2O3, 3SiO2, the chief of which is uwarawite. This is of a magnificent emerald green colour, translucent at edges and of a vitreous lustre. When heated on the borax bead it gives an equally beautiful green, which is, however, rather more inclined to chrome than emerald. This is an extremely rare stone in fine colour, though cloudy and imperfect specimens are often met with, but seldom are large stones found without flaws and of the pure colour which rivals that of the emerald in its beauty. The fourth variety, D, is the lime alumina garnet, its formula being 6CaO, 3SiO2 plus 2Al2O3, 3SiO2. Like the others, it has a number of sub-varieties, the chief being the cinnamon stone, which is one of great beauty and value when perfect. This stone is almost always transparent when pure, which property is usually taken as one of the tests of its value, for the slightest admixture or presence of other substances cloud it, probably to opacity, in accordance with the quantity of impurity existent. This variety is composed of the oxides of aluminium and silicon with lime. In colour it ranges from a beautiful yellowish orange deepening towards the red to a pure and beautiful red. Romanzovite is another beautiful variety, the colour of which ranges through browns to black. Another important variety is succinite, which gets up well and is a favourite with jewellers because of its beautiful amber-like colour without possessing any of the drawbacks of amber. E, the magnesia alumina garnet, 6MgO, 3SiO2 plus 2Al2O3, 3SiO2, is somewhat rare, the most frequently found being of a strong crimson colour and transparent. This variety is called pyrope, the deeper and richer tints being designated carbuncle, from the Latin carbunculus, a little coal, because when this beautiful variety of the noble garnet is held up between the eyes and the sun, it is no longer a deep blood red, but has exactly the appearance of a small piece of live or glowing coal, the scarlet portion of its colour mixture being particularly evident. The ancient Greeks called it anthrax, which name is sometimes used in medicines today with reference to the severe boil-like inflammation, which, from its burning and redness, is called a carbuncle, though it is more usual to apply the word anthrax to the malignant cattle disease which is occasionally passed on to man by means of wool, hair, blood clots, etc., etc., and almost always ends fatally. A great deal of mystery and superstition has always existed in connection with this stone, the invisibility of the bearer of the egg carbuncle laid by a goldfinch, for instance. F. The manganese alumina garnet, 6MnO, 3SiO2 plus 2Al2O3, 3SiO2, is usually found in a crystalline or granular form, and mostly in granite and in the interstices of the plates or laminae of rocks called schist. One variety of this, which is a deep hyacinthine colour, though often of a brown tinted red, is called spessartine or spessartite, from the district in which it is chiefly found, though its distribution is a fairly wide one. The lapis lazuli. The lapis lazuli, sometimes called azure stone, is almost always blue, though often containing streaks of white or gold colour, the latter of which are due to the presence of minute specks or veins of iron pyrites, the former and colourless streaks being due to free lime, calcite, and other substances which have become more or less blended with the blue colour of the stone. It has a vitreous lustre, crystallises in the first or cubic system, and is a complex substance, varying considerably in its ingredients in accordance with the locality in which it is found, its matrix and the general geological formation of the surrounding substances, which may, by the penetration of moisture, be brought to bear upon the stone, thus influencing to a great extent its chemical composition, so that we find the stone composed of about a quarter of its substance of alumina, or oxide of aluminium, silica to the extent of almost half, the remainder being lime, soda, sulphur, and occasionally traces of copper and iron. It is mostly found in granite and certain crystalline limestone rocks, in fairly large masses. It is of great antiquity, figuring extensively in ancient Egyptian history, both in its form as a stone and ground up into a pigment for the decoration of sacred and royal vessels and appointments. When so ground it forms the stable and magnificent colour genuine ultramarine, which is the finest and purest blue on the artist's palette, but owing to its extremely high price, its use is not in very great demand, especially as many excellent chemical substitutes of equal permanence are obtainable at little cost. The turquoise. The turquoise is a pseudomorph. See Chapter 4, Cleavage. In colour it is blue or greenish blue, sometimes opaque, varying between that and feeble translucency, though it should be said that in all forms, even those considered opaque, a thin cutting of the stone appears almost transparent, so that the usual classing of it among the opaque stones must be done with this reservation. In composition it contains about 20% of water, about a third of its substance being phosphoric acid or phosphorus pentoxide. Sometimes nearly half of it is alumina, with small quantities of iron in the form of variously coloured oxides, with oxide of manganese. The great proportion of water, which it seems to take up during formation, is mostly obtained in the cavities of weathered and moisture-decomposing rocks. Its average formula may be said to be Al2O3P2O5 plus 5H2O, and sometimes Al2O3FeOP2O5 plus 5H2O. It must therefore follow that when the stone is heated, this water will separate and be given off in steam, which is found to be the case. The water comes off rapidly, the colour of the stone altering meanwhile from its blue or blue-green to brown. If the heat is continued sufficiently long, this brown will deepen to black, while the flame is turned green. This is one of the tests for turquoise, but as the stone is destroyed in the process, the experiment should be made on a splinter from it. This stone is of very ancient origin, and many old turquoise deposits, now empty, have been discovered in various places. History records a magnificent turquoise being offered in Russia for about £800 a few centuries ago, which is a very high price for these comparatively common stones. Owing to the presence of phosphorus in bones, it is not uncommon to find in certain caves which have been the resort of wild animals, or into which animals have fallen, that bones in time become subject to the oozing and moisture of their surroundings. Alumina, as well as the oxides of copper, manganese and iron, are often washed across and over these bones lying on the cave floor, so that in time this silt acts on the substance of the bones, forming a variety of turquoise of exactly the same composition as that just described, and of the same colour, so that around the bones there eventually appears a beautiful turquoise casing. The bone centre is also coloured like its casing, though not entirely losing its bony characteristics, so that it really forms a kind of ossified turquoise, surrounded by real turquoise, and this is called the bone turquoise, or odontolite. End of chapter 15. Recording by Kevin Green. End of the Chemistry, Properties and Tests of Precious Stones by John Mastin.